Hi, this is Alex from devstories.eu. AlphaFold, Protein Structure Prediction, Episode 18 of 21. You spin up a massive multi-million-dollar cluster with 1,000 GPUs to train your model, but your utilization flatlines. Your entire distributed ring grinds to a halt because a single machine drew a highly complex evolutionary sequence and needs 100 seconds to generate an alignment. Overcoming communication imbalance is how you fix this exact bottleneck. The underlying issue here is known as the straggler problem. In distributed training, every GPU in your cluster processes a local batch of data. At the end of a training step, all GPUs must reach a synchronization point to share their gradients. Your cluster only moves as fast as its absolute slowest machine. As detailed in the ScaleFold paper by Zhu et al., preparing training batches for protein folding is highly variable. Some amino acid sequences are short and simple. Others require massive multi-sequence alignments, taking up to 3 orders of magnitude longer to prepare. A fast batch takes a fraction of a second. A slow batch takes 100 seconds. If you use the default PyTorch data loader, it generates batches in a strict deterministic order. If one of your data loader workers gets stuck preparing a massive sequence, the training process waits for that specific batch to finish. Even if other workers have already finished preparing subsequent batches, the pipeline is blocked. Your training step finishes, your local GPU goes idle, and because it cannot reach the synchronization point, the other 999 GPUs in your cluster sit completely idle waiting for it. The ScaleFold authors solved this by building a non-blocking data pipeline. Instead of enforcing a rigid sequence, the pipeline yields a batch the moment any processing batch becomes ready. Here is the key insight. The system decouples the data preparation order from the data consumption order using a priority queue. First, you assign multiple data loader workers to prepare batches asynchronously. When a worker receives a batch to process, the system tags that batch with its original sequence index. This becomes its priority score. Let us trace the logic. Worker 1 gets batch A, a fast sequence. Worker 2 gets batch B, the 100-second sequence. Worker 3 gets batch C, another fast sequence. Worker 1 finishes batch A immediately and pushes it to the priority queue. The training process consumes it and executes a step. Worker 2 is still crunching the massive batch B. Under the default system, the GPU would stop and wait. But in this non-blocking pipeline, worker 3 finishes batch C and pushes it to the queue. Since batch B is still not ready, the queue simply hands batch C to the training process. The GPUs continue training without a pause. Eventually, worker 2 finishes batch B and pushes it to the queue. Because batch B has an earlier original index, the priority queue immediately places it at the absolute front of the line. The training process consumes it on the very next step. This priority mechanism guarantees a best effort sample ordering. The exact global sequence of data changes slightly across different training runs, but the paper confirms this does not negatively impact training convergence. You eliminate the idle time caused by background CPU usage peaks and complex data samples. The slowest data batch no longer dictates the execution speed of your fastest machine. That's all for this one. Thanks for listening, and keep building.